Hello everyone, welcome back to lecture 33. So, we will continue our discussion how we can utilize the geospatial technique in liquefaction studies, right. So, we have seen that in microwave domain we are using mainly the DINSAR, that is differential interferometry synthetic aperture radar, and the coherence image, right, which is generated from microwave remote sensing. These two are used in liquefaction study. When we talk about the differential interferometry of synthetic aperture radar, the single pixel of SAR image consists of two parts, the amplitude and the phase. And the amplitude gives us the idea of the intensity of the signal which is reflected from the surface, the backscattered energy, and the phase is used to detect changes. Now, here we will be utilizing these two concepts together to identify is there any subsidence or this structural deformation or the surface deformation on the surface. So, here when we talk about the phase, this is how we calculate the phase. So, we are interested in the phase difference of two images. So, which is giving you the information about the change in the surface because of the soil. Okay. So, the phase difference is basically governed by the shift of the ground surface from one location to another location, and it will be in centimeter or millimeter, it is not that high. We get the phase difference, so back calculation gives us the ground deformation. So, using this we can calculate the phase difference and then we will get the difference in the ground deformation. Then we calculate the coherence. So, here INSAR signals decorrelate due to random motion over time, differential geometric and volumetric scattering, right. That will give you the coherence. This is also used to determine liquefied surfaces. So, this has been utilized in various studies to identify the liquefiable zones. Here you can see the coherence image result from Sentinel-1C data. So, this is using the microwave remote sensing to identify the locations which are susceptible to liquefaction. The green stars in the location, here you can see the green stars are the locations of the epicenter, and the red dashed line shows the approximate areas of the sand blow associated with liquefaction. So, here this is the sand blow area. So, in this particular paper they have nicely explained this process. Coherence reduction area between the pre and post earthquake pairs are indicated by white dashed lines, right. So, here you can see some of the white dashed lines are there. So, when we talk about the optical remote sensing, the pre and post earthquake images are identified and then downloaded and pre-processed, and which will help you to detect the soil moisture by various approaches, right. And liquefied locations are identified from moisture change in soil due to earthquake. So, pre and post you have two images, right, and then you will go with the soil moisture mapping, and then you will see which are the hot spots which are giving you the drastic change in the soil moisture because of an earthquake, right. So, normalized difference water index is one of the very popular method which is used to identify the moisture content, right. So, this NDWI Gao, it is developed by Gao et al. So, here you can see the NIR band of 860 nanometer. This we are talking about the optical remote sensing, right. So, remember 400 to 2500 nanometer we are using here. So, this is 860 nanometer, and then we are using another band which is 1600 nanometer. Then we have again 860 and 1600 nanometer in the denominator, so that we will be having the normalized differential water index, right. And NIR is near infrared, SWIR is the short wave infrared bands. This is another indices which is NDWI green SWIR 1. Here we are utilizing 550 nanometer and 1600 nanometer, and then again in the numerator and denominator we are using the same to provide the normalized difference, right. So, in another index it is green and SWIR 2, here it is 550 and 2200 nanometer. So, these are popular in identifying the soil moisture condition. Here you can see the Zhu et al, they have given this modified one. So, 560 nanometer and 1600, and here you have 560 nanometer and 860, right. So, this will not be the normalized one, but this is MNDWI Zhu, right. Then comes the temporal differential liquefaction index. So, TDLI, this is very popular. So, here what we do is pre-earthquake SWIR band, right, that is been used, and then post-earthquake SWIR band. So, here you can see both places we are using 2200 nanometer wavelength range, and then in the denominator we have 2200 nanometer pre and then again post. So, it will be normalized one. So, this will provide you the temporal differential liquefaction index. This will try to provide you the information about the pre and post earthquake event, right. Then you have delta index. So, index post earthquake and the pre earthquake, which is calculated from here, and then this will provide you the delta index. So, that will provide you more information about the location. Then comes the tessel cap wetness. It is a statistical method. Statistical analysis is used to come up with an orthogonal transformation that would capture the wetness difference, right. So, for the pre and post earthquake. This transformation was produced by Huang et al. 2002 based on hundreds of field measurement of soil, impervious surfaces, dense vegetation and moisture content. So, this was an extensive study where they have utilized many field observation data to come up with this tesseled cap wetness, right. So, now we will see some of the case studies. So, here first we will talk about the Tripura region, then we will have the Egypt, and then we will have Madhubani, and these are published literature. We will see some of the details so that you will be having an idea how geospatial techniques are used. So, when we talk about this optical remote sensing, reported liquefied locations are georeferenced in the study area. Different geospatial techniques are used to get moisture change due to earthquake for the study area, and then the result from geospatial techniques are compared with the results from the literature to find the best technique. This was a comparative study, and here we try to evaluate different approaches of remote sensing, how and which one is giving you the best result. So, this is for the first case study, which is for Tripura region. Here we had magnitude 5.2, and then in 2017 we had this 5.7, right, and here the depth of the epicenter was given, and this is the time and date of the earthquake. So, significant earthquake in Tripura since 2010. This is from USGS earthquake catalog, right. So, liquefaction feature in this study area, you can see this is how it is appearing in the field. So, this is from this particular paper. You can see these surface cracks after the earthquake event, right, and here you can see some changes in the soil also. Reports from this paper show that the river Manu's current course has shifted from its original course. This is the older river alignment, and this you can see this is the new one. The distance from the current course and the liquefaction feature is approximately 124.5 meters, right. So, this is the Google Earth image of the liquefied site from this particular paper. So, in this what we did is we used the USGS Earth Explorer to get the pre and post earthquake images, and then it was converted to reflectance. Then we did the normalization, and then these two different approaches, one is Tessel cap and another is different indices which is available, that were used to identify the moisture content, right, or changes in the area. So, processed pre-earthquake image, that is for 2016 December, and this is January 2017. Then here again for the same date, right, and from both we are getting the image difference, and that will try to give you what are the hot spot of that particular region. Here you can see this is from the NDWI GAU pre and post earthquake, right. So, I hope you can see the changes, right. Here you can see the minimum and maximum, minimum and maximum. This is the image difference. I told you that image difference will give you more information about the study area, right. So, this is the liquefied site which is from the field or from the published literature, and here you can see the minimum and maximum value, and this can provide you more information about such area which is getting liquefied. So, this is NDWI Zoo pre and post earthquake image. Here you can see the minimum maximum, how it is getting changed, and then you have the image difference of NDWI Zoo, right. So, here you can see the changes, and this is the location. This is the Tessel cap wetness and pre and post earthquake image. So, here you can see this is the pre. So, this is the range and this is the range, how it is changed, right. This is the liquefied location. This is the difference delta Tessel cap. So, here you can see the minimum maximum, and this is the liquefied zone. So, this is one example how remote sensing different approaches can be used to develop a method to identify the liquefaction potential zones. So, this is another study from Egypt. So, the 1995 Gulf of Aqaba earthquake left its mark in the vicinity through ground and structural failure. This is from Halim et al. 2004. Possible liquefaction caused ground deformation was observed along the coastline near this particular city, especially in the hotel areas. Ground fissure even as wide as 10 centimeter were reported. So, this was huge. These failure caused major economical drawbacks and decrease in the tourism, right. So, here for the earthquake we had the moment magnitude of 5.5 and the date was 27th June 2015 and the focal depth was 22 kilometer, and here you can see this is the location, right. So, here again the pre and post earthquake images were accessed through USGS Earth Explorer, and then the DN to reflectance was converted. Then we had the normalization, and then similar to previous study there were different geospatial techniques that were used, and then we identified the image difference. So, different geospatial techniques were used to identify the surface changes. So, here you can see the city and the earthquake. This is the earthquake. So, here you can see the extracted SAFE file from the Google Earth. Here there is the SAFE, and then for this particular study area, right, you have Tessel cap witnessed image, and here you can see the minimum maximum value. This is for NDWI GAU, again the minimum maximum you can see. This is NDWI green SWIR2, so that I have discussed in the previous slides. Then you have the NDWI green SWIR1, the values you can check. TDLI of the region of interest. So, here low and high value, this is the city, right. Then you have NDWI green and IR of the study region, then study area along with the liquefied sites. This was an example how we can evaluate the potential of geospatial technique in liquefaction studies. So, it is not only that we go with the field based or the lab based analysis, we can also look for an alternative by which we can identify the liquefiable zones, right. So, this is another case study from Madhubani, right. So, here you can see the study area along with the liquefied sites. So, this is India and here you can see this is the Darbhanga, and here you can see zone 1, zone 4, zone 2, zone 3 for the liquefied sites, right. So, here what we did is we applied the geospatial techniques, we utilized different methods to estimate the image differences, and then we classified the image differences into 3 classes and then extracted the higher value pixels, right, and those were indicating the liquefied zones. So, here the image difference from 5 geospatial techniques, first one the A, it is Tesselt cap wetness, B is NDWI GAU, then NDWI green NIR, then D is NDWI green SWIR, and the E image, this one is NDWI green SWIR2. So, you can see how different they appear and the ranges how it is changing when you are having different approaches, right. So, the comparison between the pixel with the highest moisture change and liquefied location from literature corresponding to NDWI GAU image difference. So, here you can see the image difference. So, this star is giving you the liquefied location and this blue color is the pixel in class 3, right. Then again the comparison between pixels with highest moisture change and liquefied location from literature corresponding to NDWI green NIR image difference, right. Then this is from NDWI green SWIR1, right. This is from NDWI green SWIR2, the same approach, right. And then comparison between pixels with highest moisture change and liquefied location from literature corresponding to Tesselt cap wetness image difference. So, here you can see for each of the location how the Tesselt cap values are coming, right. So, the conclusion is Tesselt cap wetness index is a suitable technique to find liquefaction related moisture change in soil. At least for Darbhanga region it was very clear, and the limitation is cloud cover in data, because we are talking about the optical remote sensing. Then the vegetation cover in the area, because this optical remote sensing, when we talk about 400 to 2500 nanometer, it gives you the surface characteristic. If your area is having the vegetation will act as a surface and the surface will reflect the energy, and that you will be calculating. So, you will be getting the reflected energy from these vegetation, and the rainfall in between the period of pre and post earthquake image acquisition, that will change the wetness condition, as well as that will also restrict to be captured this optical remote sensing data. So, when we talk about the geospatial technique application, so liquefied areas are mapped. So, you have historical data sets, you can collect also, and then you can put them into star, and then you can overlay over the satellite images. So, liquefied and non-liquefied data set is prepared using different band ratio, Tesselt cap, and then the proxy parameters can be investigated, right. So, the proxy parameter is not the direct parameter which is playing critical role in the liquefaction, right. But since we have limitation with the remote sensing, we can also look for the proxy parameter. Those can have the impact on the liquefaction study. So, model can be developed on the basis of these proxy parameter, and that will try to help you to identify the liquefiable zones. So, existing models are from Zhu et al. 2015. So, the proxy parameters for 3 main factors like soil density, soil saturation, earthquake loading was chosen. Soil property has not been included in this particular work. So, they did not consider this, but then they have used the logistic regression to develop this Zhu et al. Model, right. Then probability of liquefaction is calculated using their model, and they have also validated it. So, a global model and a regional model for coastal region was chosen. The parameter in global models are PGA, CTI and VS30. The parameter in regional coastline models are PGA, CTI and ND. So, you can see here this legend. So, PGA is your peak ground acceleration, CTI is compound topographic index, VS30 that is shear wave velocity of the top 30 meter of the soil, ND is the normalized distance. So, these were utilized to develop the regional and the global models, and they have again come up with this 2017 model. So, 23 additional earthquakes from USA, Japan, Taiwan, China and India were added to make a model more accurate. Both liquefied and non-liquefied incidences were considered to omit sample biasness. So, this is what they have done. They have improved the database and then they improved the prediction. Incidents were classified into 2 categories like coastal event and non-coastal events, because we are talking about the interaction of water, even it is surface water with the soil, right. So, that is reducing the shear strength. So, these are the references you can see here, which I have been referring in this particular slide. So, if you are interested, you can go through them. That will help you to understand the application of geospatial technique in better way. Thank you very much.